All right, so we're going to get started. Welcome everyone to our Maryland Robotics Center seminar series. It's a lot of S alliteration sounds. So welcome. All right, so today we have Professor Mosadegh from the Weill Cornell Medicine. So he got his Ph.D. his BS and MS in Biomedical Engineering from UC Irvine, followed by his Ph.D. in the Takayama Lab at the University of Michigan, Ann Arbor. And then did a postdoc at Harvard, the Wyss Institute, under the guidance of George Whitesides. And so for me personally, actually, the reason that I am here is actually likely because of his work. And so there was a big paper that was first authored by our speaker back in 2009, demonstrating microfluidic circuitry in these really interesting circuits. I had never done microfluidic circuits in my life, and I was like, that is cool. I want to do that. So then for my postdoc, I started doing that. And then it was like there was kind of no killer application for that type of work. And so when I interviewed here, I actually said I wasn't going to do any fluidic circuitry work anymore. And then another paper that our speaker co-authored came out in Nature with the Octobot, making use of the fluidic circuitry. And I was like, I'm back in the game. And then I started doing soft robotics based on fluidic circuitry. And then for the first time in my life, I was doing robotics. And then I got invited to be part of the Maryland Robotics Center. And now here I am, getting to host these seminars. So, welcome, and let's give a big round of applause for our speaker.
Thank you for the kind introduction. So, the first thing I want to talk about really is actually this huge gap that really exists in my career, I would say, of starting out in microfluidics, microfluidic logic circuits, doing 3D cell culture systems, and then now I'm working on like AI, VR, mixed reality, image guidance for like surgical. So it's this like massive gap, and I thought maybe I'd quickly just go through like how I evolved kind of like do that. So, you know, starting out in microfluidics, studying just how cells move, then doing my PhD, which was an incremental move, I would say, in the sense of it still was working with microfluidics, doing advanced logic circuits with that. And then it was during my postdoc that I was then working in these like three-dimensional cell culture systems, and that's what my main project actually was. But while being in the group, on the side, it was like they were building these soft robotic systems, and I thought, oh, that's kind of cool. And when I thought about it, really was the soft robotics was very similar to how you would build these microfluidic systems, where you had silicone, you pour it over a mold, and it really was just a difference in scale. So then I actually kind of made a bunch of different projects from that. But it was that project that actually kind of landed me my assistant professor job, where they wanted to make medical devices from these soft robotic systems. And that's what really got me into the Department of Radiology at a medical school. And then through there, it was actually working with these 3D printed systems that got me into like how to do image processing and going from patient-specific designs to making these types of devices that got me then to understand, well, then how do you do then image guidance systems using all of that sort of 3D segmentation and imaging systems. So that sort of describes how that happens. So you can see that really between these different shifts, there are these very specific kind of missing link technologies that lets you kind of slowly evolve from one type of research field to the other. So what you think you're working on now, you will be very surprised of how you can apply that to new fields, and you will find yourself doing very different things over a course of like a decade or so. Right now, I'm the director of the Dalio Institute of Cardiovascular Imaging. We work on a myriad of different projects that you can roughly bucket them into like diagnostic technologies, interventions, training, and even like working towards benefiting the patient experience. So of these projects, I'm going to talk about these 6 during today's seminar, and I'll just sort of jump into them chapter by chapter kind of during the talk. So the first one is going to be this cardiac mapping catheter. This really is a marriage between my background in soft robotics and then another professor, Simon Dunham, who came from John Rogers' group, who does a lot with stretchable electronics. And so this really encompassed both of our backgrounds to do this. So for patients that have arrhythmias, there's really 2 types that we are tackling right now. One of them is atrial fibrillation, the other one ventricular tachycardia. For AFib, essentially it's really, really prevalent. You know, patients over the age of 65, 10% of them will get affected, over 150,000 deaths annually. 20% causes for strokes. That's a 5 times increase for the risk of stroke, 2 times increase in the risk of death. And then for these minimally invasive procedures that they try to treat this, there's actually only a 50% success rate at a 1-year outcome from it. So relatively low success rates for this disease. For ventricular tachycardia, it affects 3%, which is still a large population, but it has 450,000 deaths because these are actually sudden cardiac deaths just because your ventricle is so important for making sure it pumps blood to the rest of your body. And now these outcomes can be better, but the procedures themselves are actually very difficult to do because the way they do it is when they want to do the procedure, they will induce the arrhythmia. And because it's actually so dangerous, they're on a clock. They have to actually complete the procedure really, really quickly. So being able to do it fast is super important. So this gives you a sense of like how they actually do it, where they get these catheters, they navigate them into the left atrium of the heart, and they're mapping the electrical activities to try to understand where they actually need to do the treatment. And the treatment in this case is they're actually burning your cardiac tissue in order to stop the electrical activities from going like chaotic and haywire. So a lot of these end up happening from the pulmonary veins. So there's pulmonary vein isolation is a very typical way that they do it, but they don't always only originate from these veins. So being able to find where these other sites are incredibly important. Now, open surgery, they have high success rates that are kind of like at 80 to 90%. But this is, again, open heart surgery where they're cracking open the chest using bypass, and it's highly, highly invasive. And patients that are much older really don't have an option of having this type of invasive procedure. So these minimally invasive procedures are quite important, but your outcomes are significantly lower. So the idea is how do we do a better job of figuring out where these arrhythmias are occurring? So there has been this push for making devices that have more electrodes and able to actually be able to map the full chamber simultaneously. The reason being is that AFib is considered to be this chaotic arrhythmia where they don't understand in space and time where things are happening. So when they have to have a catheter that is going around the chamber and mapping it at one given time doesn't actually necessarily mean it's the same type of arrhythmia at a different time. So that's why they kind of have these really poor outcomes. So they started to make these basket catheters, which actually fill up their entire chamber, but they really didn't work well. The reason they didn't work well is, one, they're using nitinol, which in the medical field is actually considered to be this like highly elastic, alloy and should kind of be highly conformable, but it's still like 1,000 times stiffer than a polymer that you could use. So what you end up seeing is that maybe you're only getting 40% of the sensors actually making contact with the cardiac tissue. The other thing is they have something called spline bunching, where it's the rigidity of these splines that actually cause them to want to bunch into different crevices of the heart, and it becomes difficult for them to actually get it to go to the full surface of the heart. So these were a couple of reasons why this device ended up not really being effective. So really what we wanted to do was kind of mimic that general shape and approach, but use soft robotics to make a highly conformable device that can have many electrodes all over it. So the first thing that we needed to do was actually make highly thin types of actuators so that they can actually fit within the catheter and then be inflated and then expand sort of like in the left atrium itself. So we kind of started to use this method where we get thermoplastic polyurethane sheets. You actually just put them on top of each other, and you can use a laser cutter to actually just cut and weld at the same time. And then you can use this to make just very like simple actuators from it, but you have very, very thin sheets. And so this was different from the more traditional way that we had done it by pouring and molding silicone on 3D printed molds. And so the cool thing about it is you can just kind of change the laser pattern and get very different types of shapes and actuators, and all this can be done in maybe a couple minutes to be able to go from a design to like an actuator. So it's also like very rapid prototyping, which is also very nice. Using kind of also the laser cutter, what we can do is get flex PCB, where that can be made actually at scale. And then what you can do is use the laser cutter to raster around it, and you can get rid of that kapton layer, and then you can render these electrodes to be highly stretchable. So something that normally is just flexible, you can change it to be highly then stretchable by removing that inelastic kapton material and then incorporating the traditional serpentine patterns for your electrodes so that you can achieve that. And the way that really works nicely is that there's this sort of like auto alignment or masking that happens, that it's the copper material itself that is the electrode traces, that when the laser passes over it, it acts as a heat sink. So it protects the kapton layer beneath those traces, and then the rest of the kapton gets obliterated away. So if you got rid of all of the kapton altogether, the copper would be too brittle and that would just break itself. So this allows to find this happy medium where it has enough stability that you can utilize it, but gets rid of enough kapton that it still ends up being a stretchable material. So this is just kind of demonstrates how we're able to then integrate these flexible electronics into those soft robotic actuators. So you end up with these like bending beams that have the electrodes all along it. You can either do this as like different pairs where you can then measure bipolar electrograms, or you can do them as single and have higher densities of electrodes as then monopolar electrograms. These are sort of like showing that we're able to just get high mechanical robustness through many, many actuations. You know, this type of procedure, it's a one-time use of the device. You probably would only actuate it maybe a few times, but you can see here we can go to hundreds, and we're able to get good electrical signals from it. We did some characterization to make sure that we can just get electrograms by doing this in a rabbit heart, and that worked out nicely. And then we wanted to actually integrate this into a larger device where this kind of leverages then kind of the origami effects, where you can have all these things in a single sheet and then fold them to actually then make this sort of full chamber 8-leg device. And this had then 128 electrodes on it. We had this on like a 3D printed handle, and then we did this in a pig study. Well, this just shows it like dynamically moving in these like in vitro hearts. And then, sorry, I should have skipped it, but, and then we characterize essentially how much actually these electrodes come into contact with them. So within these 3D printed heart phantoms, what we did is we did a micro CT, and then we actually showed how many of the electrodes are actually within a couple millimeters, which is enough to get an electrogram to show it. And so we saw that we can get at least 80 to 90% of the electrodes in contact, whereas the traditional basket catheters were getting 40 to 50%. And then when we put them into the animals, this is in pig studies essentially, we're able to see, it's very difficult to kind of see it within these ultrasound images, but we essentially, the nice thing was, because this is still kind of a relatively hollow device, we're not impeding the blood flow. And a lot of the physicians, when we showed them this device, that was their biggest concern. We're like, it's so big that you're probably going to mess up things, but we didn't. And so within the atrium, that was sort of expected that it would be fine. But what really they had concerns with was actually in the ventricle, because the ventricle, you have the mitral valve. And they really thought that it would just mess up its ability to actually work as a valve. However, what we found, and if you kind of pay attention to this part here, you can actually see that it's the valve itself hitting and knocking our device out. So that's really the power of this being so soft that the heart itself doesn't get impeded, where it's actually able to contract as it would normally, and the valve is able to move as it wants normally. Whereas if we had these nitinol devices, that would be so rigid that it would keep the leaflets from actually coapting properly. And then, so the next step was actually to integrate this then on a minimally invasive catheter. So we actually just got commercially available Oscor sheaths and catheters, and then physically kind of just you could see just like kind of taped them on and got them to be there. And then these are on essentially catheter sizes that can be used clinically. And then we wanted to actually show that we can do a transeptal approach. So this is where you enter from the IVC through a femoral axis, and then you actually cross. And they do this normally clinically, where you make a hole between the right atrium and the left atrium. You pop the catheter in, and then you can actually deploy your device both in the left atrium and the left ventricle. And so this is just demonstrating that we're able to do that. And again, for here, we're really just demonstrating that for safety reasons, we're actually not going to cause any hemodynamic instability. And so all that kind of worked nicely. You can see that the leaflets, they still don't get interrupted, even though we have our catheter also going through the leaflets itself. And then we're able to get electrograms from all of the sensors all together. And so that was like a big success in showing that at least the performance was working as well. This is kind of demonstrating why we think this kind of has value clinically, is just because our ability, because these devices are so soft, that you can just twist them and they will naturally then contour to the surface itself. So this really makes a big step where now they don't have to individually articulate the catheter to go point by point along the surface. You really can just deploy it, spin it, and then within a matter of hopefully seconds to minutes, will be done. Whereas now it takes several minutes to, sometimes they have to go back and do it many times, and that can take even hours. So for ventricular tachycardia specifically, this can be a really big game changer, where they really want to induce this arrhythmia as short as possible. So we have spun this out into a company. It's called Conform Medical. And really the idea is to be able to commercialize this device where we're just going to make the device itself. We're not doing anything in terms of the mapping system itself. But what we're trying to demonstrate is that this device, because it's actually so sort of dynamic, is that we can do the pulmonary vein isolation. So you can see now it's actually fitting inside the pulmonary vein and able to actually do the whole chamber mapping when it's in its big shape. In addition, being able to actually get it to also fit within the ventricle, where normally these devices are primarily used just in the atrium itself. So future work with this is really just working with manufacturers to kind of convert this device from us making it on the benchtop to actually being a scalable process. Doing more preclinical studies to actually make sure that the catheter handling design itself is actually done well where clinicians find it to have high usability, and then making sure that we can actually integrate this with already commercially available cardiac mapping systems so that they can do the diagnosis that they're doing. Future directions kind of in the research phase of this is right now we're only doing like mapping of the device, but as I mentioned, the therapy for this is actually a different catheter, which is to deliver energy either through RF, radio frequency, or pulse field ablation, which is kind of like electroporation. And that's, we technically should be able to do that through the same electrodes that we have. So you have the ability then to just map the device, find where you're at, and then actually deliver energy also to do the treatment. There's no reason also that we can't just like on these electrodes and put other types of, different types of sensors, whether, we're going to do nuclear sensing through PET or things like that to be able to actually just have multifunctional then diagnostics within them. So I'm going to sort of shift gears now to this patient-specific LAA occluder device. So for patients that have these arrhythmias, one of the big problems is that they get stroke. So 90% of those the strokes that occur, they actually occur in this feature that's called the left atrial appendage. It's this small sac that hangs off of the left atrium, where in most of the textbooks maybe that you saw, you never even saw this. So it's only in like the medical books that they show. It's like, oh no, the anatomy is even more complicated than you thought, and there's this little pouch. So because the heart becomes stagnant during these arrhythmias, then blood actually starts to clot within them. And the problem is that if that clot actually embolizes, that's what's actually causing the stroke. So what people really want to do is actually plug that, just totally plug it and let it re-endothelialize, where it then just comes sealed off. Now the difficulty with that is everyone, kind of almost like a fingerprint, their left atrial appendage has a very different shape, size, anatomy, and it's really, really heterogeneous. But the devices, due to kind of like regulatory, restrictions and requirements, usually just have a single shaped device. They're usually round, and they have to try to just get these to plug within these different anatomies. So what they ended up have a lot of clinical studies to show that there actually were worse outcomes that happen later on with leakages that actually occur. So it's like they plug these devices, the blood is still able to occur in some sense that can increase the risk of these. So it sort of defeats the purpose of having these devices. And the big reason why you want these devices is people don't want to be on oral anticoagulants because there's risk for bleeding, particularly for these older patients. So what we really thought was, well, from CT scans, you know exactly what the device, what the left atrial appendage looks like. So you can just design a device that perfectly fits your anatomy using 3D printing and a patient-specific design. So that's what we tried to end up doing. First, we want to just show that that the patient-specific design itself is helpful, because you could think that you could just have a round spherical device, inflate it, and eventually get in. And what we ended up seeing is, no matter what, as you start to inflate something, it wants to round out. And what becomes very important is that actually the interface of the ostium, the device to the essentially the crevice of that left atrial appendage, you want that to be as smooth as possible so that the hemodynamics of that make it such that it doesn't become a nidus for clotting. So this sort of demonstration here shows that you get a lot less of that happening when you actually have this patient-specific design versus these spherical ones. In addition, by making it match the anatomy itself, it also means you can actually inflate it less, which then makes the device more robust. So we actually demonstrate these in large animal models. We're able to go through the full process, deploy it, and show that it actually is able to perfectly fit into the anatomy of the device. Now, when we had done this, and this was probably I'm trying to think, maybe 6 or 7 years ago actually, the field, when we had started it, there was no FDA approved device. By the time we actually got through the research side of it, there was already a company that got FDA approval. Now, what ended up happening is this idea of leaks are bad. They did a lot of clinical studies, and it was shown that leaks actually weren't that bad, that there weren't worse outcomes. But the way that they did the studies is they actually looked at very short time points, and they only did these at centers where it was like very good physicians that were very diligent on how they deployed these. But now that it's been several years later and these devices are being deployed in many different types of hospitals, studies are coming out showing that, oh no, leaks actually are a big deal. And if you look out even farther in terms of outcomes, it becomes worse. So this is where we're now excited again to be able to deploy it. And kind of almost the reason for bringing that anecdote up is a lot of times you get feedback about things where, I don't know why I skipped, but you get feedback about things of like, oh, this is no longer relevant, but oftentimes you really need to dig into the kind of the motivations of where publications come from, because a lot of times there's a lot of biases through there. So if you kind of intuitively understand and know that something kind of is real, kind of trust your gut in that regard. Instead of trusting always the literature, which is a very antithesis of kind of what it means to be a scientist, but you kind of realize later in life that it's like, oh no, this is a very blurry lines. So I'll through that project, what we ended up finding is that we by making this patient-specific device, what we ended up needing to require of the physician is now they had a device that wasn't circular, it had a shape and design, and that means they have to actually deploy it in a correct angulation and orientation. So it's actually much more difficult than what they usually are. So we felt that we needed to actually make a better guidance system in order for them to know exactly what angle to be able to deploy these devices. So that's what kind of got this project started. So, with cardiac interventions as like a minimally invasive procedure, it's becoming more and more needed just as we have actually an aging population. And complications in these procedures, you can see that there is actually this like learning curve for when physicians have to learn how to put in these devices. And when complications are at you can see it goes from 3 to 9%, like getting close to 10% for a minimally invasive procedure is actually quite high. So these are all things that want to be addressed. So one way to do it is to think of how you can provide better imaging for the physicians to understand where the devices actually are when they're doing it. Currently, right now, the standard of care is using fluoroscopy and ultrasound to guide them during these procedures. Now, with fluoroscopy, the thing to note is the heart itself is not actually visible. You only see your tools in this open, gray space, and it's only through the use of contrast agents that they puff that then is able to opacify the structure, that they're able to build an intuition for where they are. In addition, they have to constantly change the angle at which they're taking these x-rays to be able to then, in their minds, be able to map out in 3D where the device is. And then the good thing about ultrasound is you can see the device, but it actually has very poor image contrast, and it requires a trained operator that usually is a completely separate person than the interventionalists themselves. So it requires a lot of coordination for them to actually understand. So the newer methods that people do is try to leverage fusion imaging, where they actually get preoperative CTs. They segment those structures and try to overlay them on the fluoroscopy, but these still don't give any sort of quantitative feedback. It obscures the fluoroscopic image that they're actually trained to interpret, and it's still only this 2D projection for where they're seeing. So there's no depth perception that's actually intuitively within it. So really what we're trying to leverage is we can use the 3-dimensional imaging to be able to guide people and provide quantitative feedback for that. So because of all the sort of new innovations that's happening but with extended reality, for cardiovascular interventions, there's still not much that has been done. What they have been doing is really more on pre-procedural planning and education and training. And the reason it's kind of difficult to do intra-procedural or a real-time guidance is really because the heart itself is this constantly moving through either its contractions themselves or through respiration. It then becomes very, very difficult to actually do those types of motion compensations. But this is really our attempt to actually, sort of do this. So this is a real, scene that was built out in Unity. It's like a game engine where we're tracking the position of the catheter. This was done in a 3D printed heart phantom. And we're essentially with fluoroscopy, actually then segmenting where the catheter is in real time, and then co-registering it to what would be a preoperative CT, essentially, of the cardiac anatomy. And because you can set targets pre-procedurally, you can then in real time also then calculate what is the distance from your catheter tip to any given target for a procedure that you would want to do. And the whole idea is that you would see this within the XR headset. So, for us, we're still seeing it as a 2D projection on the monitor, but when you have it in the headset, it would be a true 3D rendering that is being shown. So clinically, the way that this would work is that a patient preoperatively would have a CT scan. There would be a 3D segmentation that is done. And then during the procedure, you would use fluoroscopy, and you would get real-time images of where your catheter is in it. Now, because the spine is present in both the CT scan and visible in fluoroscopy, you can co-register then these two coordinate systems based off that intrinsic fiducial marker, which is the spine itself. As like a, one of the goals that we really want to do is make this a vendor-neutral system. So there's a lot of capital equipment that has to go into buying these C-arms and fluoroscopic units, that it would be very, very difficult to try to get people to then buy new systems to replace it. So what we really want to do is be able to actually use this as just an add-on to current existing systems. So the way we're doing that is we're just streaming the fluoroscopic images that are being taken by these systems, and then being able to process those in real time using AI. And then simultaneously taking through wireless ECG and respiration sensors on the patient, using that to then do the motion compensation that allows our sort of like visualization to look stable, but it's actively actually compensating as we're updating what the coordinates are itself. Now this project is fairly expansive, and there's a lot of like sub-projects within it. So one is just doing the deep learning for actually doing the real-time catheter detection. The other is then the co-registration algorithms themselves and getting those accurate using the spine as a fiducial marker. Now this is kind of in some ways application specific. There would be other applications, like if you're working on the coronaries, where you could just probably use the coronaries themselves in order to do it. Just because those are things that they do puff contrast constantly, and it's a fairly expected anatomy, I would say, compared to what you're doing with the preoperative CT. And then, the motion compensation is just a whole other project as well, of how do we do sort of these interpolations between where the heart is during these respiratory cycles and the cardiac gating, and have that actually occur in real time. The other big thing is, right now the way that we're doing the tracking, and it's working very well, is we're leveraging these more advanced systems that's called biplane imaging, where you can take two x-rays simultaneously at different angles. So that makes it very trivial to know what the 3D position is. However, most cath labs only have one C-arm itself, so you can only get one angle itself. So what we're trying to do is train AI models to be able to either guess what that other angle would be, or to directly interpret where they think that it is in the Z-plane. So this kind of just shows our evolution of being able to train different AI models to be able to do the catheter tracking. We first had started out with kind of the very traditional UNet. The reason we kind of wanted to move away from it, even though it worked actually very well and it didn't really need that many images to train, is that it still would mean that for every new catheter and everything you would actually just want to have a set of images that someone has to annotate, and making those ground truths can be somewhat tedious. In addition, we're actually then feeding in these like images into our system, and that's actually quite heavy. So what we really wanted was to be able to have a model that ended up just taking the input image and only giving coordinates that could then be fit to a spline. That would be within the Unity scene. So that way it can allow us to actually have something that has a lot less latency within the system itself. And so what ended up really working well is actually doing object detection using the YOLO model. So surprisingly, it's by just actually picking the different parts of the catheter, the object detection is able to find those relative positions, and all you do is just take the center point of that object, and that's actually what we feed into the splines for the Unity scene. The other thing that we worked on was some catheters actually had the need for like the roll angle, so 6 degrees of freedom for tracking. So we started to train AI models that actually can interpret what roll angle it has, and that ended up working out pretty well. And then what we really wanted to do is really test with users to know, is the mixed reality something that's actually beneficial or needed? So what I mean by that is the depth perception that's provided by these XR headsets. Does that provide benefit over just having navigation from this that would be shown on a monitor? So the way we did this was just have users do a certain set of tasks where they're just manipulating the catheter to get to different targets and track their speed. And then we had them do that when they're using the XR headset, but they actually only have like 2D views within that 3D environment. we did a combination of having both 2D and 3D available, and then only 3D available. And as you can see, there's a kind of a 3 times difference between the 2D and the 3D. And somewhat interestingly is that the 3D still did better than actually the 2D. They were having both 2D and 3D. And the reason for that is actually just a matter of focus. That people ended up, when they had more options, their mind kind of constantly goes between the two. And if you just give them sort of like the ability to just do one thing, they actually can do it much quicker. So that was like a very positive, feedback. And I should say that this was all done with, like they were essentially lab members, students, things like that. And so no one actually had experience with like intervention. They weren't physicians. They had no experience with catheters themselves or these types of tasks. So when we did another, I thought I put it in. Well, I didn't put it in, but we have newer data that's actually taken with physicians. And what we ended up finding there was it was much more, inconclusive, I guess I would say, that the 3D is actually better. So what ended up happening is we saw that like physicians that actually have training, like these are more like electrophysiologists, that they are used to seeing 3D visualizations, they did better with the 3D. And then other physicians that actually only see these 2D monitors through the fluoroscopy, they did much better actually just on the 2D. So it shows that based on your prior experience, that what ends up being actually easier for you to use is just kind of based on that. And what we found overall is the people that end up doing the best is really how much do you actually play games normally, like fundamentally. So all of this is going to go into like how you kind of want to design a system, providing options for different users. So these are sort of the physician feedback studies that we want to do, whereas before everything we've done is kind of just to interpret whether the 2D versus 3D is important. What we really want to prove actually is that the navigation system in and of itself is actually better than the standard of care. So we're going to do that by having these 3D printed models where we have actual physical posts and targets where then they can actually physically try to get their catheters to actually go to those targets and see how accurately they can do that versus just the speed by which they can do that. So we're going to switch gears now, and this is talking about uterine fibroids. So, even though we're a cardiovascular institute, a lot of the technologies that we're using can be applied to many different fields, one of which can be women's health. And so, uterine fibroids is the most common benign tumors that exist. You'll find that like 70% of women will have uterine fibroids by the age of 50. This is also a very common impact on pregnancy. And really, that is also one of the biggest impacts of which surgeries you end up actually deciding to undertake for this. And it has a huge economic burden. Now, in addition, it's also that the types of treatments that get chosen is either these hysterectomies where you would remove the entire uterus itself, or myomectomies where you go in and try to remove only the fibroids and keep the uterus intact. And the primary reasons for this would be for making sure that, impacts on hormonal levels or the desire to maintain ability to have pregnancies. So depending on what's your choice based on the procedures you have, there are several different options for different types of options of these procedures. So and they range kind of from these very open surgeries where you would go in, and literally the surgeon will use their hands to actually use a scalpel and like remove the fibroids themselves. The benefits that has is they can physically feel with their hands where the fibroids are located, and usually they can take out all of the fibroids or most of them, and it's the easiest for very large fibroids also to be removed. And this can go all the way down to like these hysteroscopic methods where they actually will have through the cervix, they will actually put a device that then will have a needle and they try to stick it into the fibroids themselves and then sort of ablate them and have them be removed. Intermediate opportunities that can be used are UFE. This is uterine fibroid embolization. This is where you actually will inject different types of particles and they actually will go and specifically actually block and cause ischemia in the fibroids themselves. The nice thing about that is that, it happens to all the fibroids simultaneously. However, because it's, in some ways not going to be too specific to the fibroids, there's risk of also damaging the healthy uterine tissue itself. So typically people who want to maintain their pregnancies, this would not really be an option. So the way that people decide of which of these options really can do, it's really like has a lot to do with how many fibroids you have, where the fibroids are located, and they will do this based off of diagnostic imaging. So ultrasound is the most common way to do it because it's fast, cheap, easy, but MRI really provides you the most state-of-the-art solution because it gives you a really holistic 3D view of where all the fibroids are. But in both of these cases, you have a radiology report that's provided and it's interpreted by a radiologist, but given back as actually a text-based report. So the referring gynecologist, typically they're not really actually analyzing the images all that much. They're trusting and looking at these radiology reports, but they have no images, and typically because of time restraints, I would say, oftentimes, even if someone has like 20, 30, 40 fibroids, usually only 3 to 5 of them will be listed on these reports. So they're still making these clinical decisions with the patients themselves without kind of all the information. So during these consultations with the patient, a lot of them, they will just doodle out, okay, this is kind of what's happening, or they'll show the MRIs. But, even for physicians themselves, it can be difficult to interpret these images. So really what we want to try to do is actually provide a 3D holistic view of where these are. In addition, you have the surgeons themselves that usually they're going off of memory of where these fibroids are, and they don't actually have any maps or anything during the surgeries. And again, if it's an open heart, they can feel it, but for these minimally invasive procedures, they really are just going off their memory. So the problems with MRI, though, is that these fibroids can be presented on different which are different layers or slices on the scan. So even though it's kind of considered to be a 3D imaging modality, it's actually only presented and shown in these 2D ways. So that can lead to misdiagnosis or missing of fibroids. And if you have those issues, it really leads to longer surgeries and higher blood loss. So what we really started to make was this end-to-end solution where you would have essentially the ability to make these 3D renderings from the MRI itself. And then this is all stuff that, again, really exists in other fields very routinely, but it really doesn't actually exist in women's health. So that's the purpose of kind of creating this solution. So for patient counseling, patients would be able to look at these, have a very intuitive feel of how many fibroids they have and why they're choosing certain conditions. For preoperative planning and decision of what type of surgery to do, hopefully the physician is able to actually get a better sense of what's actually the burden to make that decision. And then also during the actual surgery, the surgeon can then look at these in real time and be able to leverage it. So that's what we first looked at, was its ability to actually improve outcomes during surgeries. So we did a pilot study with 20 patients. What we really wanted to look at was operating times and conversion rates and blood loss. And then we just wanted them to general satisfaction of the surgeons using surveys. Now, what ended up happening was there was actually really no real improvement based on the study in both blood loss and the duration of the procedures. The reason being, though, is that when you're I was there for all of the procedures, there's so many other factors that ended up going in where maybe an equipment broke and they have to just wait 20, 30 minutes, for someone to bring it in. So there's all these things that we didn't sort of take into consideration that really mitigated that as being it. So we're not too, even though this this wasn't able to positively show that this is impactful in the procedures in that way, it did what ended up actually occurring was that in our control group, there were 0 repeat procedures, whereas in the test group, we had 3 repeat procedures. And why that ended up happening was actually the interpretation of these MRIs before these procedures. They actually didn't necessarily understand or know where certain fibroids were, and that meant that after the procedures, they had to go back and actually do them again. So where we really see that there's a potential for this is to actually do better planning for these procedures. But generally, as we did the surveys, everyone sort of agreed or strongly agreed that this was quite useful. So this kind of gives you a sense of kind of the types of 3D renderings that you can get from this and why they're able to actually then avoid any of the complications that normally wouldn't necessarily occur if you didn't have this type of visualization just based off of the MRI itself. Future directions with this is to actually also, instead of just showing these on tablets and monitors themselves, actually show it within mixed reality headsets. What made this actually harder to do, and we haven't implemented it now, is most of the headsets now, the battery lives just aren't that long, they're very bulky, and so while cardiac interventionalists are kind of happy to use this because their procedures are much shorter, usually like 15, 20 minutes or so, and they're used to just standing and looking at a monitor themselves. With the surgeons, these are like 4 to 6 hour procedures. They're constantly moving around and everything, so it's much less practical. So as there's improvements in the hardware for XR technology, this is going to become something that's going to be much more easier to actually adapt. And the other future directions really is actually automating this process. Well, right now, when we did our pilot study, we manually segmented the uterine fibroids and we presented that into the 3D renderings ourselves, whereas what we really want is an end-to-end solution where you can just upload the MRI and you would automatically get the 3D renderings made. So we're working on training this UNet model to do that segmentation. All right. And then for the last project, it's on this stenosis detection problem. So this is for dialysis patients. So essentially, there are 400,000 patients. They are getting dialysis usually 3 times a week. Now, 25% of these hospitalizations are due to vascular complications. So this is actually when you make these AV fistulas, essentially a stenosis is going to eventually occur. Now this will happen to all patients eventually. There's really kind of no way, at least now, to sort of prevent them. So really it's a question of when is it happening and how do you prevent it. The reason this gets a little bit complicated is, one, they've done many, many clinical trials where they're hooked up to these dialysis machines, they have pressure sensors, everything. None of those have been effectively been able to actually properly diagnose whether you have a stenosis in it. In addition, when you go in to actually get your angioplasty to open up that stenosis, the unfortunate reality is you're actually more likely to have a re-stenosis of that. So you're sort of kind of put into this downward spiral. Now, what that means is that you really want to try to have as little of these procedures as possible. So it's not like people can kind of be very cavalier and just if you think that it's going to be the case to just get the procedure. Unfortunately, we also live in a reality where a lot of people make a lot of money by doing procedures. So oftentimes what ends up happening is that patients get referred to actually have these procedures, and once they're on the table to do it, they usually just do it. And it's only really, really sort of like ethical physicians that are doing it, that if they do the angiogram and they see that they don't need it, that they will not do the procedure. So it becomes very important in the clinical field to have reliable screening tools to be able to understand who needs it, because you still need to actually act quickly if you're going to have a stenosis. So the way that we wanted to do this was to actually use a digital stethoscope to actually get sound files from the patient and then use AI to interpret whether or not you have a stenosis based on that. Now the reason we wanted to use a digital stethoscope is that this is actually an easy enough tool that the technicians at the dialysis centers can't operate these, whereas right now if you do something like even ultrasound, getting good images and interpreting those images is still kind of too difficult for that to be done at scale. So that was the reason for doing that. So the way that we were able to do it was we actually got 6 different locations along the arm, and we got sound files from all 6 of those, and we trained an AI model to be able to interpret whether there was a stenosis or not. What we ended up doing to kind of get this to work is that it didn't really work well when we actually analyzed the sound files themselves. So we actually had to pre-process these, and we actually switched them to either get these spectrograms or recurrence plots, and then we actually ran different AI models that actually used those as the inputs, and then we compared their accuracies as well. Now we also tried to look at non-AI models, and none of those worked as well. So it really showed that even though when we kind of looked at it, it felt as if there were criteria that you can kind of tell between a patent and stenotic ones, but whenever we ran it, essentially the error bars are so big that there's no one given rule that will work for kind of all the patients themselves. So again, we trained CNN models, we trained ResNet models, and also vision transformers, and then we did those comparisons. And what you can see here, that through the models, it really is just when you actually look at these individual locations separately with different models that we can get relatively high accuracies for them. Whenever we tried to make universal models that tried to guess it for all different locations, accuracy drops significantly. And again, you can see here at the bottom that the non-AI approaches also did very poorly. Now, what's, in terms of this like 90% accuracy of how it works as a screening tool, because you can see before here, we really don't get up to, for all of their locations, 90%. But for a given patient, what you really only want to know is that if any one of the given locations is going to show you a positive result, you take that as something as a positive that they should actually go get screened. So when you take it with that criteria, then we end up having a 90% accuracy, which matches the accuracy of what a trained nephrologist can do themselves. So for that, that's essentially what we've done, and I'm happy to ask any questions. Questions from the group?
I have a ton of questions, actually. Great presentation. It was really, really good. I guess my first one will be, so I saw you had a pipeline going from a CT scan to a 3D model. And I wanted to ask, what was the fidelity on these smaller blood vessels? Like, what's the smallest blood vessel that you can detect on the CT scan in terms of diameter, and it will be accurate in the 3D model?
Yeah, so for this particular project that I showed it in, we're really only focused on structural heart intervention, so we're just doing the chambers themselves. So we do have other projects where we are focused on the coronary arteries. So from there, it becomes very important of like getting different branches and things like that. So I would say, I'm trying to think exactly what the number is, but probably from like, 1 millimeter, I think is probably around where you're going to get. Now, there are newer technologies that are coming out, like there's photon counting CT scans that are going to push that down a lot more. So this is all based off of the regular CT scans that are available.
I had a question about the modeling of the uterine fibroids. So you said, I just got a bit confused on the side. So the physicians really liked it, but there were no like quantitatives, but they still really enjoyed like having that as an
Anecdotally, it was them being like, this should be a part of every procedure, because for them, it was very comfortable to be able to refer back to it.
Okay.
But again, quantitatively, in the way that we designed the trial, there was no benefit in terms of the duration of the procedure itself or the amount of blood loss, because the blood loss and the duration kind of go hand in hand together in a lot of ways. But what we ended up finding was, again, the amount of repeats procedures that had to be done. That was where there was something. Again, this was only 20 patients, so you can't conclusively kind of say it, but this suggests that it's worth doing a larger clinical trial to be able to assess whether that's the case. So if anything, the minimization of repeat procedures is a much kind of bigger finding and more important than the procedure itself kind of having individual improvements.
Okay. Makes sense.
You said for the AFib soft sensor detection, you're trying to find like a specific position, electrical signal, and time, right? So
yeah.
if you spin that sensor around, how do you make sure that you pick up every single time? Because it might miss one as it spins around.
It's a good point. So we're not holistically kind of getting everything all together, and there has been some technologies that have attempted to do that. This is somewhat of that compromise where, because, the way that they're doing it now is they're going very slowly kind of around. So there's like, the idea is that if we're able to do this in a matter of seconds, that hopefully it is the same arrhythmia that you're doing, such that those kind of assumptions are there. But you're absolutely true that it's possible that we still would have some issues with that. One other way to make it work is, you could get a bigger catheter that would have more splines such that you can cover the whole surface area and do it all at once. But for now, we're sort of sticking with this approach.
You mentioned some software in Unity. My first question would be, is it open source? And my second question would be, is it also a physics engine? Like, does it accurately represent the blood vessels, like elasticity, if one thing bumps into the other?
It has the ability to do that, and so it is available. I would say so it's free to use. I think as long as you're not using it for commercial purposes, so definitely can. It does have some physics engines. I don't know if it won't be specifically, I think, for like material properties. Those are probably things you have to like input into it with like different scripts and things like that. But it does have things like collision detection and all that, because it really is meant for like game, as like a game engine.
And what was it called again?
Unity?
Oh, I meant like the specific software, or is it just?
Oh, Unity is the software. Okay. Yeah. So.
Great talk.
Yeah.
So yeah, I have a question about the catheter for the ventricular fibrillation. So is it soft in terms of being soft for the LV, left ventricle, and also right ventricle? Because the right ventricle is really, really soft as a
For sure.
wall, right?
Yeah.
So it works well for both. And then would that be able to be more patient specific in a certain sense, right? Could that be designed like also to know where the mapping is going to be more important in a preclinical setting to then accelerate? Because it's a really long procedure.
Yeah, totally. And yes, I would say answer kind of shortly is yes. That this is, I think for both of the right and left ventricle, it's still considered to be because again, it's even softer or like more compliant, I would say, than even the leaflets itself, which is quite thin. So definitely I think it should work with there. And yes, and it's patient specific in the way that because it's quite conformable and your ability to change the length of it, of how much gets deployed, was what allows it to kind of be a one device, one size fits all.
Okay. Great.
So for the first project you presented for the AFib sensor, my understanding is that the system currently doesn't have any tracking system to track where the electrode is in the chamber. But my understanding, like the procedure, ultimately you need to know where this irregular signal is coming from, and it's hard. Any idea like how that tracking will come?
Yeah, so what I meant to say is we're not developing our own tracking system.
Okay.
We will use the commercially available. So right now I think there's like 4 tracking systems. 3 of them are proprietary, where like you can only use it with the device that it's being sold with. Abbott actually has one called the Insight that is an open source one. So you can make your system work with that, where you have to kind of one by one get all of your electrodes and you just plug it in, but then it's able to be fed in. So, but we will use their system.
Okay, so the tracking is not based on any kind of information provided by your.
It
system.
kind of
it's
is.
Kind of like looking for that.
No. It actually does impedance. So the way that it works is that you put just different electrodes on the patients, and then it just makes an electric field, and then you're able to each of those individual sensors actually know where you are in 3D space.
Oh, I see it. Okay.
Yeah. But that's all using, again, the already available system.
Thank you.
Sorry, another question, kind of building off of that. For steering, were you just essentially doing the normal way where they just kind of wiggle it, or was there sort of active control?
For the catheter, you mean?
Yeah.
Yeah, so we're just using steerable sheets to do it. So it's very coarse movement, essentially. So the idea is that our device is big enough and soft enough that it can just kind of conform to the shape of and then you're just roughly getting it like kind of centered using the steerable sheets.
So this is a data sets question. I saw you trained a couple of models. You fine-tuned a YOLO model, and then I think also a vision transform model. What was the size of the data sets that were needed to be hand-labeled for those models?
So the UNet, I'm trying to remember, it was super small. It was like 100 images or something like that. Like actually very tiny. We were surprised kind of that it worked as well as it did. And honestly, in reality, I should have just kept with that and like moved forward. But like, almost just like to make it like it didn't seem elegant enough. So that's why we spent a lot of time and effort actually getting the other models to work, and those needed thousands of images for the object detection actually to work well. But like it probably wasn't necessary in terms of like getting to a sufficient solution so the project as a whole moves along. But I think that's the beauty of academics. You can like make art where it's just like. Yeah.
For your second project, the uterine fibroids research, what was the ultimate like intended impact for that research? Like, because I was kind of confused on what the goal was.
Yeah. So this, I mean, when you say ultimate goal, like, I would say the way that it started really was it was a surgeon who came asking like, hey, can you help with this image guidance? So she really wanted that to occur. So that was the original goal, was can we actually just kind of solve this issue of they don't have any guidance during the procedure, which seemed very straightforward because again, a lot of this already exists for other types of procedures. So that was the intended goal there. And then, but it's kind of through doing the studies that we're noticing that even though it's a nice to have, it's not really a game changer or must have for those procedures. So what we really think is the real benefit that is going to change kind of clinical practice is actually for the referring gynecologist to be able to look at these, understand them, and change which procedures they actually would decide on. So, but even that's a hypothesis. Like we still need to actually tests to understand whether that's actually going to provide benefits. The hard thing about that is it's very hard. There's no way to know if you change the procedure for that given person whether or not that would do it. So you have to do very, very large clinical trials, and that takes a lot of time and effort to be able to do. So.
Awesome. Let's give a big round of applause for our speaker.
Thank you so much.
Gift for you.
Appreciate it.
Hopefully it doesn't make your bag go over.
Oh, yeah. It'll be fine.
But if you have any additional questions, feel free to come up. We have a few more minutes before our speaker's next meeting. Otherwise, thank you so much for coming. This was awesome. I think hopefully for a lot of students this was a bit inspirational as well, that maybe what you're working on right now in your PhD could be totally different than what you end up doing with your career. I think, and to being open to that and knowing that you're not like necessarily pigeonholed in exactly what you're doing today. Which, if you enjoy it, that's awesome. But if not, know that there's like these completely different tracks that you can kind of branch into. So let's give one last round of applause, and we'll see you all soon.